Hello and welcome back. In this video, we're working through an example where we're going to determine the equation of a line of intersection of two given planes, Q and R. So first, imagine you have just two planes in space. What can happen between those two planes? Talked about angles between them, things like this. The two planes could be parallel, in which case they will not intersect at all, and we won't be able to find such an intersection line. Or if the two planes are not parallel to each other, then they will intersect at a line. So the first thing I'm going to do here is just jump over to GeoGebra and graph these two planes. So I have the equations of the two planes. I've entered them into my calculator here, x plus 2y plus z equals 5. I'm going to go ahead and turn that one on. So that's the first plane, P, looks like that. And then let's see the second plane, 2x plus y minus z equals 7. I've entered that in already. And you'll notice these two planes intersect each other along a line. Now, one function I can use in GeoGebra is to just intersect. So this is intersect path. That's fine. I just put in intersect and then the two equations. And so I'm going to turn that on, and that gives me the intersection of the two planes. I would like to recover the equation of this line. So how do I get this line? GeoGebra does it for me. You can see it's giving me an equation down here, but we'd like to do this by hand just to better understand the geometry of these vectors, of vectors and planes and things like this. So how do we get a hold of that intersection line? Well, one thing I'm going to notice here, and actually this will work with any of the coordinate planes in this case, is these two planes both intersect the xy plane, where z is equal to 0. So you notice that? If I just look at the intersection of each of these planes in the xy plane, that will give me two lines. So I'm going to find two intersection lines first, and then, so that's the idea. I'm going to find two intersection lines first, and then I'm going to find where those lines intersect, and that'll give me a point that's both in both of the planes and in the xy plane. And that will then be on the line of intersection. So what I'm really trying to find here is the point on this intersection line that goes through the xy plane. That's what I'm going to start with. Because as you'll remember, in order to find an equation of a line, what do we need? I like to start with this sort of basic problem-solving strategy is figure out what we need to find an equation of a line. We need a point on the line, and we need a direction vector. V, and I'll call this one, I don't know, P naught. That's doesn't need to be a vector. We just need a point on the line and a direction vector. So as I mentioned, to get a point on the line, one way I can do this, and there are many different ways we can do this, one way is I'm going to look at the intersection of each of these planes with the xy plane, because that's really easy. So to find when a plane intersects xy plane, so remember the xy plane, the z coordinates are all 0, set z equal to 0 in the equation. So for Q, that'll give me x plus 2y equals 5. So Q gives me x plus 2y equal 5. What does this represent? This represents the intersection of Q and the xy plane. Right? It's easy to do intersection lines between a plane and a coordinate plane, one of our standard planes. Same thing over here. I'm just going to set z equal to 0. This is going to give me 2x plus y equal to 7, and this is the intersection of R and the xy plane. And now I have a system of equations. So now I have two lines that are both in the xy plane, And these lines are on Q and R respectively. So this is a line on Q, this is a line on R. If I find their intersection point, then that'll give me a point that's both on the line of intersection between the two planes and the XY plane. Okay, so let's do that. I see a way to do this not by substitution, but by elimination. If I multiply this first equation by -2 and add it to this one, that will eliminate the x variable. So I'm going to do that. So I'm going to do -2 times this, and then I'm going to add it to this guy. So -2x plus 2 minus 4y, minus 4y equal -10. And I'm going to add that to 2x plus y equals 7. So that's going to eliminate my x variables. I have -4y plus y, that's a -3y. And -10 plus 7, that's a -3. So that gives me y equal to 1. And then when I back substitute that, so 2x plus 1 equals 7, so 2x equals 6, x equal 3. So that tells me x equal 3. So that tells me then 3, 1, 0 is on the line of intersection of Q and R. Right? Why is this z coordinate 0? Right? It should be clear where I got the 3 and the 1 from. Why is this 0? That's how I engineered this problem. Is I found lines in the xy plane where z is always equal to 0. So that was, we kind of set this at the beginning and then found what x and y had to be to finish that off. So now I have a point on the line. How do I get a direction vector? How do I find a vector that's parallel to the line? Well, that comes from my normal vectors for these two planes. So I'm going to call them NQ, normal vector NQ, and normal vector NR. Remember, we have those bits of information. So NQ, remember how I can read that off? It's the coefficients. The normal vector for Q is 1, 2, 1. And the normal vector for R is 2, 1, -7. Whoa. No. 2, 1, -1. 2, 1, -1. So the idea is these two normal vectors, each one is normal to its respective plane. And so if I can find a vector that's normal or orthogonal to both of these, then that will go along the line of intersection. Let me maybe jump to the GeoGebra again and just take a look at that. So I have so imagine my normal vectors coming out of each one of these planes. This line of intersection needs to be orthogonal. Since it's on both planes, it must be orthogonal to each of those two normal vectors. And so that's the idea that we're going for. We're just trying to find a vector that's normal to both of these. And so to do that, we do a cross product, as we have done before. So let me maybe do this over here. So let me just say, I guess, direction V is orthogonal to both NQ, because the intersection line is in the plane Q, and anything in the plane Q is orthogonal to NQ, and NR. So we're going to compute NQ cross NR. This is a standard trick we'll use time and time again. To get a vector orthogonal to two other vectors, we compute a cross product of them. So that is the determinant of a 3x3, I, J, K. My NQ is 1, 2, 1. Order, again, is not going to affect my final answer here. It'll affect the normal vector that comes out of this. But remember, any vector that's parallel to my line will do. So whether it's whether it's in the same direction as this normal vector or the negative of that, it's not going to matter. 2, 1, negative 1. And let's compute that. Again, I hope you're getting comfortable computing these. If not, keep practicing. So in the I direction, I'll have 2 times negative, that's negative 2, minus 1, that's negative 3. The J direction, 1 times negative 1, that's negative 1, minus 2, that's negative 3, but remember J gets flipped around, so that's actually 3. And then in the K, 1 minus 4, that's negative 3. Negative 3, 3, negative 3 is parallel to L. So just writing that conclusion here, and hence parallel to the line L, our intersection line. So now we have a point on the plane that was 3, 1, 0. Point 3, 1, 0. And direction, anything in the same direction as this vector will work. I'll just use the vector itself, negative 3, 3, 3. And then remember back to what the equation of a line looks like. Remember, it's my fixed point, the vector pointing to that, plus any multiple of this vector. So L then looks like, I'll call it R of t, will look like the point 3, 1, 0 plus t times negative 3, 3, negative 3. And that works as the equation of my line. So that was a more advanced problem for sure. It took a few steps to get there, a little bit of work, but it all really boiled down to the geometry of lines and planes and of the cross product. So this is a really good example for that reason. Okay, that's it for this video, and that's it for this section. So in the next section, we're going to get into some surfaces, some really fun sort of surfaces. We'll see them in the next couple of videos. All right, I'll see you there.